Okay, so welcome everyone. Thank you for attending this session in which we're going to be discussing uncertainty and its importance in energy planning. The title of the session is Uncertainty and Modeling Lessons Learned and Gaps, and that's what we're going to be focusing on. Today, we are really lucky with the panelists that we count on. We will be having Asgeir Thomas Gard from EMP-E. We're going to be having also Paula Falugi. I'm going to be introducing them later, but just to mention their names, Jeannie Bourgmont and Thomas Herti, and we will be covering the most important points about uncertainty. So if Eric, you can go to the next slide.
Yeah.
Okay. So first, we're going to be reviewing the results of the quick survey that many of you took before joining the session. And after that, we're going to have the plenary talk of this session from Asgeir, and that's titled Uncertainty in Energy Planning, the State of the Art. After that, I will be covering the view of uncertainty through 3 European projects, and that's going to be my contribution to the session. Then Paula is going to tell us about investments in transmission planning with uncertainty, and Thomas will tell us about the approach that is being currently taken and developed in the Osmos project. We'll finish with a Q&A session, and in case you want to start introducing your questions right now, you can just take the QR code that is on the screen. I would like to also warn everyone that the session is being recorded, so all the questions that you make, as well as, of course, the interventions by the panelists and myself, are being recorded. If Eric, you can go to the next slide. Okay, so basically, we are all aware that uncertainty is key in energy modeling, and that now it's not only necessary to consider short-term uncertainty, but also a very different long-term scenarios. And this combination is proving to be extremely difficult and complex, as we will discuss later. Also, the time coupling that is introduced by storage and its growing role is making things even more difficult to consider, which is compounded with regional markets. And now we have more resources than ever to accomplish this task. We have more computation capacity, but also we have new algorithms and new solution methods. And we are going to cover all that, as well as the perspective that is being taken from practice in European projects. Next. We're gonna focus on the main challenges that can be identified in the current context, and that can be, as I was saying, combining the long-term uncertainty, for instance, in the development of generation mainly, with the short-term one. Also, we need to take into account this coordination between the expansion of generation and the expansion of transmission, and always keeping reasonable computing times and reasonable resources required for the optimization. And of course, and this is a very recent focus, the replicability and openness of data and of models. Next. I would like to see this again from the perspective of the survey. So if Eric, you can open the PDF. Okay, awesome. So basically, most of the people here, we are researchers and working in academia, and pretty much everyone is quite young. So with almost 70% being less than 35 years old. And unsurprisingly, most of us are either male and working in expansion planning or public policy. Also, we wanted to take a little bit a look about the role of uncertainty in our work. And as you can see, most of us already work with uncertainty. We were curious to see whether anyone was joining who was not including uncertainty already in his or her job, and but that is not the case. And our perception of uncertainty is in general that it is a key factor to include in energy planning, and that the main problem that comes from ignoring uncertainty, I think that this is not showing completely in the screen, but the reason that most people selected as the most important one for including uncertainty was that without the inclusion of uncertainty, we need to adapt too frequently the decisions that we take. And this was selected by 40% of the people. Almost everyone said that ignoring uncertainty was either very, very risky or the most risky in their opinion. And when we were asking about what were the sources of uncertainty that were the most relevant, the highest answers were climate change and also the policy framework that was that is going to be in place. This also has a reflection of the people who are working. Remember that most of us, whether either in energy planning itself or from the side of policy making. Also, the best approach to reduce uncertainty was selected as modeling uncertainty in the decision itself. And when we were asking for the reasons, and this was something that we really wanted to look at, most answers have to do with the rightness of the approach, because we think that uncertainty is just part of the problem and has to be included in it so that the decisions that we take make sense. The method that most people use is actually sensitivity analysis. So most of us are just doing deterministic optimization and running some sensitivity analysis on top of that. Some of us do use stochastic optimization, and actually from the panel that you have today, most of us come from stochastic optimization. Dani, Paula, and Asgeir, of course, they come from the stochastic optimization domain. And then we have other methods, but they are far less prevalent. I was very curious to see how many people were using robust optimization, but it seems like only one person was using these methods. This can be very interesting for the Q&A so that you can explain what your views are on the different methods. The reason why people use the methods that they apply is mostly because they have proven to be effective by experience, and they are computationally efficient. And also there was someone who highlighted that they were open to using other methods, which is probably one of the main points of this session. Within the method, most of us are using Bender's decomposition, and there are some methods that are more preferred than others. And for instance, the introduction of uncertainty in the parameters is one of the preferred ones. Okay. Most people are working in Python, which also reflects the trend on open models. And also there are many people who use GAMS. And as for solvers, still Cplex is king, and Gurobi is growing rapidly. The simplicity is the main reason for the choices. And after this, if you remember, we asked you some specific questions about the development of the network in the next few years. And this was actually quite interesting to see that most of you thought that Central Europe will attract the greatest level of electricity and transmission investment. And also a huge majority of people thought that the cost of batteries will reduce steeply, and that the greatest sources of uncertainty with respect to demand-side response are going to be psychological effects or social effects. Also, you thought that those psychological effects that could make it more complicated could be overcome by the possibility of getting large revenues. Also, CCS was not considered to be very relevant for the future, but hydrogen was indeed. And in the as for the question on what the system will look like with respect to centralization, most of you thought that this will be mixed, but we get more responses that focus on centralized generation rather than, sorry, decentralized generation rather than large centralized plants. We have no surprises with respect to the energy relevant sectors that can contribute the most to decarbonization. So we have passenger transport and space heating. And the ones that will prove the most difficult to decarbonize are the industry, and we know that lots of technologies are being developed right now for specific industries, and freight transport as opposed to passenger transport. Also, there's a lot of division with respect to what we think the future carbon emission prices are going to be, and but most responses are in a moderate range and in the very high range for the very, very long-term future of 2050. Those were the main results of our survey. And again, thanks to everyone who contributed by filling the survey. And now I'm going to give the word to Asgeir Thomas-Gaard, who is a professor at NTNU. And he is, among many other things, chair of the Committee on Stochastic Programming of the Mathematical Optimization Society. He's an authority in stochastic programming and in energy planning. And he's also a member of the advisory board of climate for the Norwegian Minister of Climate and Environment. So thank you, Asgeir, and I leave it with you.
Thank you, Sarah, and thanks a lot for the invitation to this very interesting webinar. So I was asked to talk about uncertainty and in energy planning, and I've chosen to take a slightly methodological approach to long-term and short-term uncertainty, but will use some examples from the power market planning that we are doing in Trondheim. And I think also I narrowed it down to long-term energy models. And I think there's a number of things we could talk about, but 20 minutes is not that long. So I decided to talk about multi-scale modeling, and in particular the multi-horizon approach that we have used a lot for our modeling. That starts under assumption that the short-term matters really in long-term models. And I look a little bit into the methodology and also mention a few things about stability and how to generate scenarios. Long-term uncertainty, I will mostly show you an example and also mention a little bit about how we can solve combined short-term and long-term uncertainty models, which has, of course, the major challenge that I explode in size due to the modeling of the stochasticity. And very briefly mention something about the value of stochastic solution and as compared to rolling horizon deterministic solutions. And then in the light gray are all the things I don't have time to talk about, like long-term scenario generation, how do you generate them, and value of stochastic planning and stochastic equilibrium. But I will mention them very briefly from time to time when I go through. So next one, please. So I'll use as an example through the presentation our Empire model, which is a long-term capacity expansion model for the European power market. It has a time horizon until 2050 or 2060. Investments happen in 5-year steps. So all the investments in generation and in import-export cable and links are included in the model as decision variables. But the aggregation level in terms of geographical resolution is quite high. So there is one node per country. And it's a quite utopic model. It assumes that all the European countries are cooperating to create a cost minimizing European power system. I think there are no proof that this happens in the investment side, at least today, but this model assumes that there is an emperor that could make a decision for the whole European power system. So next one, please. And in that lies the assumption about perfect competition, cost minimization, inelastic demand in the long run, but demand response to add some flexibility in the short run. The generation capacities are aggregated. Investments happen with continuous variables, because of course when you aggregate them, they are huge. There is no Kirchhoff's laws when you build 10 gigawatts between two countries. I think we will be able to do that respecting Kirchhoff's laws, but I don't think Kirchhoff's laws will be the limitation. I think there are other factors that will come in. And what I'm going to advocate is the use of long-term dynamics and short-term dynamics. So long-term dynamics, and this is getting important when you talk about stochastic methods. Long-term dynamics is when you have multiple investment periods. So you can do a sequence of investments in a 30, 40, 50-year horizon. Short-term dynamics is what you observe when you do scheduling every hour over the next week or the next 2 weeks in order to be able to manage your batteries, to be able your other types of storages, to be able to manage your hydropower reservoirs, and to be able to deal with the wind that is not blowing in maybe 1 week, maybe 2 weeks. So this long-term dynamics and short-term dynamics, I think, are the fundament to understand when you're designing the future energy system. And of course, then you can add uncertainty descriptions to the dynamics as well. So not only one path for the next 2 weeks, you could add a number of operational scenarios. Not only one path for the next 30 years, you could add a number of long-term scenarios that would describe the uncertainty you are facing. So that's the example that I'm going to use to illustrate these methods during the presentation. We have done similar things also using times models, but I think Empire could be a good example. So next one, please. And of course, this is a picture from an island in Europe around 5 in the afternoon. The wind is not blowing, the sun is not shining for very many more minutes, and people are coming home from work. And this is the critical challenge when you want to design the energy system. You want load in terms of supply and balance to be good, also in these kind of situations, also on islands or on the European continent as a whole. And if you go to the next one, and of course, we want to respect that there are different physical possibilities and characteristics of the different European countries. This is average wind velocities, and in this case, green is good. The green areas are where it's blowing a lot, like the coast of Norway, like the North Sea, and red is not that great. But still, you see there's a lot of investments in areas that are red and yellow on wind. And the next picture is the same for solar irradiation. And I'm just mentioning this because in a model like this, it's important that you include, of course, the local geographical characteristics that matter. But of course, this is average numbers. What you're interested in practice is the short-term numbers, what happens in every hour of the day, so that you're able to balance load and supply. And in order to do that, we need to include short-term operational hours into our long-term planning models. So the next one, please. And what we do in the Empire model is co-optimization of the strategic and operational decisions. So in the top level of this figure, you see for the type of network you have to the left, you see the evolvement of different generation technologies over the next 30 years. until 2050 or 2060. And included in that optimized evolvement of the capacity investments is also the operational consequences modeled in, for example, 168-hour blocks, as you see in the lower one. And in order to do the cost minimization properly, you need to do a combined model that covers both of these horizons and preferably have the long-term dynamics handling multiple investment periods and the short-term dynamics handling the sequences of hours that will allow you to plan for wind not blowing for a week. Okay, next one, please. And in terms of mathematics, this would lead into a structure like the one I show you here. This is an example where you don't have long-term uncertainty, so the x1, x2 up to xi. They are picturing investment periods where you do the capacity expansion of generation and cables, while the orange ones are representing operational time periods or blocks of operational time periods. And you see, you can deal with short-term stochasticity in all of these investment periods, but in practice, you are doing a two-stage model where you have, from a stochastic programming formulation, an example of a standard two-stage stochastic program below. So you could put this into a traditional stochastic optimization framework. And then if you start looking at how to generate scenarios for this type of models, let's have a look at the next one and see if there are some scenarios there. I think what matters is, and this is lessons learned, I would say, it's essential to capture the correlations. And there are a number of correlations that you need to look into. Is the temporal correlation. These are the ones that will enable you to include in your model scenarios, short-term scenarios, where the wind is not blowing for a sequence of 168 hours. And that's when batteries could get into trouble. If you would say that you invest in battery to handle short-term uncertainty, well, typically that's fine if your short-term uncertainty is handled in a 24 or 48-hour sequence. If you have 2 weeks with hourly resolution, most batteries would come into trouble if the wind is not blowing, for example, for 2 weeks. So these temporal correlations are crucial. Of course, the spatial correlations, again, I will use wind as an example. If you look at how the wind blows in the North Sea or in northern Norway, it's very different from how the wind blows in southern Europe. And that means that a model like this should be able to utilize understanding of the historical correlations in order to co-optimize the management of the European system and use spatial differences as sort of a flexibility measure into managing this short-term uncertainty. And you have, of course, between the variables like wind, solar, load, inflows, you also have important correlations that you would like to model. And what's essential to capture in this setting is the statistical properties. You could look at history and you could find some of these statistical properties like expectation, variance, skewness, kurtosis, correlation, and more. So, and then one postulate that comes from me is that it's important in this short-term scenario generation to capture exactly these historical properties, but prediction power is irrelevant. I'm not so interested in having an exact operational forecast for what is going to happen with load in Norway in the 2 weeks from January 1st to January 14th next year. That's of little relevance for my strategic planning model. What I'm interested in capturing is this type of sequences that you can see in red and orange and blue and purple, which are samples that I've taken from history. And as I sample 168 hours, for example, and these are, of course, a full load series. I think it must be for Germany for a full year. And then we sample from this year what you could call representative operational scenarios with a sequence of hours, in this case represented with those colors. And next slide, please. Then we include those samples into a typical scenario tree where we have regular scenarios, and we include them as a sequence of operational nodes in the scenario tree. And we base the scenario tree on these type of samples. And in addition, we add some peak seasons. But if you go to the next one, the trick is in the details. So by doing a sequence of 168 hours, we capture the temporal correlations. By doing the same 168 hours for load, wind, solar, we capture the correlation between the different variables. And by doing the same 168 hours for all countries, we capture the spatial correlations on history. And by breaking up this after 168 hours and sampling independently, we utilize the previous 10 years of history to create an almost infinite amount of possible scenarios for the future. And in those 4 sentences, it's basically tricks on how to do short-term scenario generation for long-term planning. If you go to the next one, there is a final part to it. When we do this, we typically generate 100 alternative scenario trees. So full trees, maybe with 1,000 scenarios each. Then we calculate a score based on a measure for each of them. It could be an aggregated moment measure, it could be a distance measure, and we choose the one with the best score. And it's not clear which of the distance measures or measures that would actually give you the best quality of your scenario trees. And that's a wide open area for future research, how to actually choose what is the best scenario tree. And remember, it's an approximation of the future, not of history. So including the full history will still give you very little information about the future. In our opinion, it's better to combine a lot of these 168-hour samples to create an infinite amount of information about the future, which obviously is not correct, but it's probably more correct than a perfect representation of history. And next one, please. And in order to understand what would be the best method, we would need more research into what you could call stability tests. The 2 types of stability tests that are most common is the in-sample stability test, where we investigate whether the different scenario trees create set of scenarios that consistently result in similar optimal values. If I do my optimization with n scenarios, and I repeat the exercise with n scenarios again, and n scenarios again, we would like that if you have a stable model, that they provide more or less the same solution. And the auto-sample stability test is where we start testing the solutions from one scenario trees into what you could call the real world solution. And that's of course also a very important test if you manage to get auto-sample stability in addition. So that's the methodological part on scenarios. If you go to the next one. So just want to check how much time I have left so I can plan a little bit, because I forgot to look at my watch. 50 minutes? 5, okay. So if you look at long-term uncertainty, I think the trick is to create this combination of long-term and short-term uncertainty without the tree exploding in size. So here we have an example where you have only a few sequences of long-term, short-term uncertainty resolving. So if I have the next one, please. And the decoupling that we do in multi-horizon planning is that we say that the next long-term period doesn't depend on the realization of this short-term period. So there's a decoupling. And if you go to the next one and just do a sequence of clicks, you can see, just do a sequence of clicks while I'm talking, you can see what happens then. This is a deterministic model. And click the next one, please. And this is a multi-stage with long-term stochasticity. And next one, please. And this is we combine short-term and long-term uncertainty, and you see how it explodes in size with almost no time periods. And next one, please. And a multi-horizon tree, we take the decoupling of the short-term and the long-term uncertainty. And if you show the next one, you will see how that works. You get the decoupled short-term, so no link between the short-term and the long-term, and you can add more short-term scenarios. Next one, please. And next one. And next one. And you see the idea that you could add a lot of short-term uncertainty without trees exploding in size. So I jump to a case study where we did combine long-term and short-term uncertainty. So if you show the next one again, and we'll skip a little bit fast over the assumptions in this one because it's standard assumptions. We take EU reference scenarios and technology perspectives as input on fuel prices, demand, which is external to the model. And the next one, please. And we take we take emissions should be reduced by 90% before 2050, so the declining curve. So increasing demand, declining emissions, and then we get to the results, typical results of the model in the next slide. Yeah, so these are input in terms of battery costs, solar PV investments. We jump to the next one. I think these are things you can look over, but it's typically standard. And then you get the type of output, and you see the generation and capacity mix. And of course, then you see the benefit of using a stochastic short-term model. When you look, for example, at wind, it has 27% of the generation, 24% of the capacity. If you look at gas, it has 10% of the capacity, 26% of the generation, because you can plan the use of natural gas. If you look at solar, 46% of the capacity, 26% of the generation. So you see how the intermittent nature is important to model in terms of how you utilize capacity. Next one, please. This is the same situation without CCS. I think we jump to the next one. This is per country, and you can see the situation with and without CCS, and I think we jump to the next one. Just next one, please. Yeah, and then we can look at grid infrastructure in the next one. And you see the main problem that we are facing in Europe. Because of all this short-term uncertainty, the model suggests to build between 600% and 800% more capacity between the different countries in terms of grid. And that's because when you look at it, oops, it's a lot of jumping here. Well, I'm not able to speak this fast. But if you go a little bit back to the what looks like a scenario tree.
This is one?
Maybe one ahead. There you have it. I think there's a delay between what I see and what you see, but so I think the main problem that I'll skip the discussion of is you need flexibility measures, and grid could be one of them, batteries could be one of them, other types of storage could be one of them, but it's important to have the short-term representation to include them. Let's spend the last few minutes on the long-term uncertainty. So this is an uncertainty tree for the long term, showing different levels of ambitions in terms of CO2 emission reductions. At the top level, you have scenarios where you could emit still a very high amount of CO2, almost the same as today, and at the lower level, you emit zero. And this scenario tree is combined with the short-term uncertainty tree into this multi-scale, multi-horizon type of scenario tree. If you go to the next one, what you get then is a number of instances, and there's no time to go in detail on the instances, but I would like to point to the problem sizes in terms of rows and columns, so variables and constraints, which is 1.7 billion rows and 1.2 billion variables in the largest test instances, where you have a number of operational hours and a number of scenarios representing different ambitions of CO2 emission reductions. And if you go to the next one, these models can typically be solved by decomposition methods. In the survey that was mentioned earlier, Bender's decomposition was popular. In this case, we have used parallel computing and progressive hedging as the solution algorithm. And to our surprise and joy, it scales quite well. When you solve this kind of large-scale combined short-term, long-term uncertainty models, you can get gaps going down to less than 1% for these large-scale models with billions of variables. It has to be mentioned that the solution time is some 70 hours on high-performance computing clusters with between, well, you probably need one node per long-term scenario. And these nodes are typically quite high computing capabilities, but it's solvable and it scales. So if you go to the next one. And the next one, the question is there a value in solving this type of models? And what the model showed is that by using this kind of approach, you get the value of stochastic solutions as compared to using the rolling horizon deterministic planning. You get an improvement in value of between 5 and 10%. So that means reduced operational costs between 5 and 10%. If you think both the long-term and short-term uncertainty matters, using a deterministic rolling horizon approach, which I guess is what many planners do, as compared to a stochastic approach where you combine the two types of uncertainties, you have benefits in the order of 10% of using the stochastic models. This picture that is on now just shows you the difference between the two approaches, and you can see what happens in some specific time periods is that the deterministic rolling horizon approach, RH in particular 2045, suddenly get into situations where you have infeasible solutions. Either you cannot meet demand or you're violating emission constraints. And that's because the stochastic model has hedged towards this type of situation, and the rolling horizon deterministic did not. And now to mention, the rolling horizon deterministic model still includes short-term uncertainties. It's just the long-term uncertainty that it doesn't handle. And then to the next one. And the way that the stochastic long-term model does this hedging is by investing in storage technologies, renewable technologies, and transmission. So the deterministic rolling horizon model that doesn't deal with long-term uncertainty underinvests in flexibility measures that we would consider to be important in the short run, but turns out to be also very important in the long run. And my next few slides are just references, and I guess you will have the slides available after the presentation. So if you like, you can just have a look at the references yourself. So thank you.
Thanks a lot, Asgeir, for the very interesting presentation. I'm sure that there will be lots of questions by now, but let's postpone all the questions together until the Q&A slot. So right now in the agenda, I'm going to present what I have titled a bird's eye view through 3 European projects. So if Eric, you can show those slides. Okay, so next. So basically, I'm just going to give a very quick perspective of what has been the approach in introducing uncertainty in transmission expansion planning in 3 different projects that have been going on for around 10 years. So it's like the 10-year evolution of the state-of-the-art models through eHighway 2050, which went on from 2012 to 2015, SetNav, which was immediately afterwards, and then Open Entrance, which is still undergoing today. Next. Okay, so in eHighway, the approach to introduce uncertainty was twofold. Actually, there were 2 different approaches. One of them was the development of scenarios that, as I will explain later, lead to robust corridors. And then in parallel, there was another methodology that was based on stochastic optimization. So basically, the scenarios that were developed were, as is usual in many other contexts, a combination of a strategy, and a strategy is something over which we have control, or at least we can imagine that policies can be designed to create those strategies, and also a future which is deemed to describe the parameters over which we have no control. Combining strategies with futures, we got to 5 different scenarios, and 5 of them were selected as the most interesting, the most challenging. Next. Then the idea was that for each of those scenarios, the situation of the European power system was calculated, and the most important constraints were identified. After identifying the constraints that are basically the congestions that happen in the network, those congestions lead to the suggestions of transmission investments. And those transmission investments are then analyzed in terms of cost benefit in order to select the most interesting ones. Next. So as you can imagine, we do that for each of the scenarios, for each of the storylines, and for each of them, we got the most interesting investments, which are, by the way, defined just as at the level of corridor, because there was no computing power to see the grid in itself, but just a reduction. So basically, the approach was to see what were the investments that appeared in all the storylines or in many storylines, and they were selected as the common corridors that made sense to build regardless of what is going to happen in the future. And you can see them represented on your screen at the very right. So the ones that are in dark red, they appear in all these scenarios. Next. And in parallel, we developed an alternative methodology that was based on reducing the network and reducing the scenarios, the long-term combined with the short-term as well. We reduce everything. We optimize the network using stochastic optimization, and then we also developed a method to carry the solutions in the reduced network to the wider network. So as you can see, we go from the nodal level to the zonal, and from the zonal to the nodal. And in the image, you can see one of the output results of TEPES, which was the model that we used, and it was developed by Comillas. Next. In SetNav, something very similar was done. So now, as you can imagine, there is more computing power and there is more importance of uncertainty. We started by defining some storylines, which were called pathways in the project, and they responded to two different dimensions that had to do with whether there was diversification or a concentration, and whether there was a focus on cooperation throughout Europe or on a national focus. And we applied this to several cases and important aspects of the evolution of the system, such as the gas network or the role of CCTS. Next. So basically, in this case, instead of trying to take the generation only as an scenario, there was a focus on the coordination between generation and transmission, and so they were solved in an iterative way, trying to aim for a coordinated solution. And two models were used, one that has the focus on generation expansion planning, which is Enertile by Fraunhofer-ISI, and then TEPES. And we could see what was the interconnection investment for the different pathways, which is just what you can see in the right part of the slide. Next. Now, to finish, in open entrance, uncertainty is even more important, and on top of trying to consider this focus on the uncertainty of generation, the short-term uncertainties, of course, of wind and solar, we also want to incorporate the use of storage. So the inclusion of system operation has to be much more detailed, and including the time coupling, as Geir was saying. I really liked one sentence that you used, that the short-term uncertainty really impacts long-term planning. So that is what we want to, one of the things that we want to see in the project. So in the approach, we're going to use some representative snapshots and representative periods that capture that. And simultaneously with that, there is a focus on open entrance about open data and models. And for instance, Empire, the model that, as Geir was mentioning, now has an open version, and the same thing can be said about TEPES for performing the transmission planning. Next. So basically, just to summarize, we have gone from not being able to include stochastic optimization and just having it as a second approach within the project. As I was saying, in e-highway, the main approach was to identify those common corridors, and then the alternative methodology used in stochastic optimization was developed. But now optimization is the main approach, and uncertainty is key, particularly using stochastic approaches. We need to include larger number of scenarios, larger number of snapshots for short-term scenarios, I mean, and we need to include the coordination with generation expansion and also with the short-term operation. And one of the new issues is this focus on open data for the scenarios to be available for everyone and open models. So that's it from my side. It's not Q&A for now, because now I'm gonna give the floor to Paola. Paola Falucci is a senior researcher at Imperial College London, and her research focuses on the development of advanced stochastic optimization models, as I was saying before, and she has studied thoroughly the problem of investment with uncertainty. So, Paola, the floor is all yours. We cannot hear you.
Good afternoon. Thanks for the introduction. And you have already told part of my, introduction in the presentation. So I will talk clearly of the importance of uncertainty in solving planning problems, especially for the European network. And next, please. And the previous speakers have already given a good insight on importance of uncertainty. So here what I could like to stress more is that if we don't consider uncertainty, we can experience consistent, irreversible investment. And also the important things that there is some learning regarding the future of uncertainty. So the uncertainty is resolved with the time when we do planning. And in this case, opens the opportunity to find strategic actions. So it becomes very important to have a framework that is able to consider directly uncertainty and to determine strategic actions. Next, please. So the problem we are interested in is a stochastic optimization problem, where we minimize some risk measure of the investment cost and operation cost that are both very important. And we describe uncertainty through scenarios. And we need, a large number of scenarios in order to have a meaningful solution. And we need to describe the operation of the system with many details. Next, please. So there are, many modeling challenges in stochastic optimization that are related to at the end, the problem sites, has already been stressed, because if we want to, obtain good decisions, we need to take in account about multiple sources of uncertainty, giving, rise to many scenario trees. We need to have a detailed description at the operation level, and also we need to take in account building times. So we need models having a high time resolutions. And complexity is added from technology like storage and demand side response, which introduce more coupling in the problem structure. Also, new technologies introduce, may introduce binary variables or integer variables, and also taking account of renewables and new demand patterns, expand the operational state space has already, been well explained from the other speakers. And so we are reaching really the limits of the computational limits to solve this type of problems. And in this context, become very important to, develop and improve the composition techniques, formulation, how to convexify the problem, and also it's important to be able to select properly significant scenarios. Next, yeah, I have already told that, okay. And in the group, essentially, we work on large scale problems. Mainly for the European context, we have looked at longer term uncertainty. But we look at multiple sources of this uncertainty, and the problems becomes extremely demanding still, because also because the operational level is described in details. And we have developed 3 decomposition methods to tackle the solution of these problems, the complexity. And essentially we decompose the problems. The classical one that is called the multi-cut bender decomposition, where the problem is decomposed between investment and the operation, and the operation is further decomposed in different blocks, and it can be decomposed even if you have uncertainty at the operation level. And another technique is the nested bender, where we define a problem for each scenario node. And this technique is advantageous in the multi-stage planning, as we want, because we want to, compute, determine strategic actions. And it's effective because essentially the size of the problem doesn't depend on the number of nodes that are present in the scenario nodes. And also it can be further, enhanced with some further decomposition at the operation level. And here, this one is the hierarchical decomposition. Next. And we have, analyzed and the performance of this decomposition, techniques on a very large problems, considering multiple uncertainties, in particularly on demand growth and on the wind uncertainty on deployment in wind capacity. And we have found that it's, we get good solutions, and also we have stressed the importance of the uncertainty and also the importance of considering storage and flexible asset in the problem, because looking at a multi-stage problem with four stages, if we don't consider storage, we get consistent investment in line reinforcement in the first stages, while if we consider storage, we move towards strategic actions, and we have saving in investment cost up to 15%, as shown in the graphs below, where there is a rough summary of the results. Next, please. So for the EU model, essentially we have uncertainty in deployment in wind and solar capacity, installation capacity. We include uncertainty in storage cost and in demand growth over a range spanning 40 years. Next, please. And for the uncertainty on wind deployment, we can, see that indeed we can expect large investment in wind in the North Sea, but these kind of investment are very uncertain, and there may be a significant opportunity to integrate offshore wind generation and interconnectors project at this, in this area, to take advantage of potential significant economies of scales. And it's possible to consider different topologies with different coordination levels. Next, please. And so we identified 4 different scenarios with large wind deployment and low wind deployment. Next. And the main message was here that was important, instead of performing deterministic decision with a deterministic model, to perform decision taking account the uncertainty. And with min-max regret on the right, it was possible to take decisions that minimize the regret, and the cost was more efficient. Next. So here the key message is that consideration of uncertainty leads to more efficient investment decisions, a better management of the investment risk. From preliminary analysis, you can see that if you solve a deterministic problem for the European context, we can get a consistent stranding of asset. And the important message is also that flexible investment are very effective in dealing with large uncertainty. Next. And multi-stage optimization framework are good to evaluate the trade-off that are required to integrate different parts of the system, and to take in account about the detailed spatio-temporal aspects. But still, for the future, we need to still to work on computational aspect of the decomposition scheme for the European case. Thank you very much for your attention. That's all.
Thank you, Paola. I was just taking a note for a question. Thank you very much for the presentation. As I said, please save your questions until the final Q&A session. Now I'm gonna give the word to Thomas Hegarty. He's presenting a presentation that was prepared together with Jean-Yves Bourmod. So Thomas, he's a third-year PhD student, and he's at Mainz Paris and at RTE, and he's also contributing to the project Osmos, as you will see. And Jean-Yves, he has worked from EDF and RTE in several European projects, such as Optimate and Osmos currently. So Thomas, whenever you want.
Thank you very much for the introduction. I'll get right in. Just a brief description of the Osmos project, and that could be handy to understand what I'll be talking about. Osmos is an H2020 project that started in 2018 and will run till 2021. And we're working on the optimal mix of power system flexibility. It consists of a set of demonstrators and a pair of theoretical work packages. The work that I'll be mentioning here has been developed mostly in the latter ones. The idea is I'm going to discuss how the different types of uncertainties are taken into account in our modeling. So power system planning involves asking several different questions which vary depending on the considered time horizon. Traditionally, on timescales of several years, this is involved in determining where, when, and what one should invest in. And then on shorter timescales, the idea is basically to check whether we will be able to operate the existing system or not. On each timescale, the sources of uncertainty facing the power system planner are very different and require different modeling approaches. And I'm going to go through the methods that we use in Osmos to incorporate these different sources of uncertainty in our modeling. In our investment problem, we adopted a very traditional approach to account for uncertainty related to energy policy, the evolution of technology costs, economic growth, etc. We've used macro scenarios. The way they were designed, for a start, we apply the same principle as the European Commission. We don't consider scenarios to be forecasts of anything, but simply benchmarks against which new policies can be assessed. The key parameter which drives the differences between the three scenarios we developed are greenhouse gas emissions. This parameter in turn leads to very different rates of electrification of both heat and transport and to different electricity generation portfolios. Scenarios also have different final energy demands, reflecting rates of building installation refurbishment and different fuel prices. Although fuel use is mostly determined by emissions at this point rather than price as we move to 2050. Now, if we look, thank you. If we look at another type of uncertainty, we'll now look at the ones that are related to weather conditions. So not uncertainty related to forecasting, mind, but uncertainty in making sure that the structure of the energy mix is able to cope with, say, cold spells, heat waves, so-called wind droughts, and the like. So to ensure that the full distribution of weather-related conditions is accounted for, we use a high number of Monte Carlo years in our economic dispatch simulations, while expressing correlations within the data. I'll now briefly discuss why we find this to be particularly important. So I'm not going to go, next slide, thank you. I'm not going to go into much detail about the methodology that we used to build this, but basically we performed an evaluation of flexibility requirements on the French power system. Here the graphs show the distribution of flexibility requirements for 200 years worth of synthetic residual load data. So currently we can see there is some degree of uncertainty on annual, weekly and daily timescales, as the width of the corresponding violin plots suggest. Now, if we move to 2035, where there's more variable renewable generation, the distribution significantly increase in width as generation is made more uncertain by the renewables and demand is made more uncertain by electrification of heat and mobility. So, right, electricity balancing is more and more dependent on weather conditions. If you can just move to the next slide, I think. Thank you. So we can see the width of the distributions are increasing. So basically electricity balancing is becoming more and more dependent on weather conditions, and now we need to consider a lot more cases than we did previously. So the way we do this is through the use of many weather years, and we make sure that we express correlations within the data, whether it be temporal correlations, but also geographical, and correlations between variables, for example, between wind speeds and temperatures. Next slide, please. Thank you. So as I mentioned previously, weather conditions can also lead to uncertainty on shorter timescales when they bring in challenges related to forecastability. So now we'll look at how we're dealing with this within the Osmos project. So next slide, please. Thank you. In our first model, we perform an economic dispatch. So we previously discussed the many weather years that were taken into account. The resulting data is then fed into another model, which is able to forecast to model forecasting uncertainty. This uncertainty reduces as we approach real time, but so does our ability to activate the various means of dealing with it. To ensure that the appropriate trade-offs are made, we simulate the temporal succession of electricity markets and the potential activation of remedial actions. The objective of the work mentioned here is to try and test and compare different market structures and mechanisms. Now, if we look at a final source of uncertainty, it's uncertainty which is related to system stability, stability as in short-term stability. It's in the next slide. Right. And basically what we showed in a previous H2020 project, Migrate, it was shown that stability in a power system mainly supplied by power electronics connected units is not a blocking issue. It's in the next slide. Because grid forming allows the power system to overcome the very first milliseconds after an outage before reserves and balancing can be put in place. In Osmos, the aim of one of the demonstrators is to test practical technical solutions for grid forming in situ in parallel with the provision of other flexibility services. So now a quick word about how all these modeling approaches interact with each other in the next slide. So traditionally in power system planning, usually the assumption that was made is that long-term issues drive system development and that the rest will simply follow. Next slide. What we're trying to do in Osmos, if you can go 2 slides up, thank you. Oops. So we find that the increasing uncertainty on shorter timescales means that this assumption no longer holds. As a result, we build feedback loops between the different models, assessing uncertainty on different timescales. Regarding stability issues, we won't necessarily look into this much because of what I previously mentioned, but the practical experience that we might gain with grid forming may allow us to improve our understanding of related costs, which we could then reintegrate in our optimization. So to sum up 3 key takeaways, we need to look at an increasing number of weather conditions and express correlations within the data. We also need to be able to simulate the uncertainty close to real time that reduces as we approach real time, but also we have decreasing availability of flexibility solutions that are able to deal with it. And on the very short term time scale related to stability issues, thanks to grid forming, it shouldn't be too much of a problem, and we can afford to kind of ignore this in our power system planning exercise. That's all for me, thanks.